Hi again, statistics students. Thanks for tuning in for our video. This week, we're kind of about rules for probability. And as we discussed on Monday and Tuesday, we talked about the OR rule, or the rule for adding probabilities. And today we're going to talk about the AND rule, which is the probability rule we use for when we say the words AND. So like OR rule was for the probability of A or B, the addition rule. The AND rule is a multiplication rule. So when we say the probability of A and B, we're going to multiply them together. It also hinges on a very important idea, which we talked a little bit about earlier this week as well, which is independence. And I know we talked about what it means to be independent in class on Monday or Tuesday, depending on when I have you. But I want to talk about first about what it means if they're not independent. And so by that, I mean, if I draw a card from the deck of cards, okay, and I want to know then after I draw that card, if I don't replace it, then what's the probability of the next card being, say, an ace? And so as we start to think about that, we develop the idea of, if they're not independent, then there's something called a conditional probability. Now, if you remember back a couple of chapters, we talked about a conditional distribution with the marginal and conditional distributions of things. And so, yeah, that's basically the same idea. And so the way it works is, the conditional probability, we usually would say like the probability of B given A has occurred. Now, there is a shorthand symbol for this. I'll cover the other shorthand symbols here in just a second. The symbol for that is just a vertical line, B given A. And so what we do with a conditional probability then is we say, okay, so given that A has occurred, now what is the probability of B? Okay, so if you want to imagine my deck of cards again, if I said, well, I would like to know the probability that I draw an ace given I drew, let's say, a 5. Okay. Well, normally the probability of ace is 4 out of 52. But since I am saying, well, given the first card I drew was a 5 and I didn't replace it, then my probability has changed to 4 out of 51. So that's what we mean by a conditional probability. Okay. The conditional probability depends on what happened in the first round of the event. Okay. If I, have independent events, okay, then it doesn't matter. Okay. Independent, as we talked about earlier, if events are independent, then the probability of B given A is the same as the probability of B. It doesn't matter that A happened. I think back to that warm-up question I asked you on Monday or Tuesday. If I roll a 6-sided die, okay, it doesn't matter what I roll. The probability of getting this twister spinner to come up, right foot green, is still 1/16. Okay, and if I roll a 4 on the die or a 3 on the die, the probability of right foot green is always going to be 1/16. That's independent. Okay, but for conditional probabilities, we have to pay attention, because we have to know, okay, so if we're not replacing something, or if the events are dependent, then how does that first event happening impact the second event? And that's what we call conditional probability. Now, I mentioned some shorthand. There's some other shorthand that you need to know. So let's add a slide here. When we're doing the OR probabilities, okay, A or B, we did that earlier this week. The symbol for that is kind of a rounded, elongated looking U. So that's probably A or B. Okay. I've said it before, but mathematicians, we're kind of fundamentally pretty lazy. We don't like to write out words, even though 2 letters versus the symbol, whatever. Okay. So I gave you the one for conditional given. The one we're talking about today, A and B, has a symbol as well. Probability of A and B. It's basically take the OR symbol and flip it over. And so that's a shorthand symbol that we'll be using as we go through some of this stuff today, and I'll be using the or symbol as we go along for some of the ones that we'll look at that use the or probability as well later on. The way I remember it, honestly, is that for the and one, it looks like an N, looks like the letter N. So it's like and. So the N sound is represented by that. I don't have a good one for the or, I just know it's the opposite. So there you go. All right. And what we're looking at today, since, you know, or was what we did earlier, right? That was the probability of A plus the probability of B minus probability of A and B. Okay, there you go. That's the general rule for the or rule, or for the addition rule. Today we're going to talk about the probability of A and B. And the way we find that is it's the probability of A times the probability of B given A has occurred. And that's how we figure out our probability for the and rule. You multiply the two probabilities together. Okay, so I know it's a little confusing because when you were learning back in like 5th, 6th grade, we taught you that in math, when we say and, like, you know, we say, okay, what's the sum of 5 and 7, right? Or 5 and 7 is 12, right? Yeah, well, unfortunately for us, and is going to be our cue. That means we're multiplying. Okay, now, if you're thinking, well, you know, hey, on the previous page, we talked about independent events, you'd be right to be thinking that. Because if we're talking about independent events, okay, well, then remember, the probability of B given A is the same thing as the probability of B. So we can actually rewrite our and rule and say, oh, well, that's actually a lot easier if they're independent. A and B is just probability of A times probability of B. Okay, and that does shorten it up quite a bit, but they have to be independent for that to work. So you'd better make sure that your events are indeed independent, because if they're not, well, then it runs into some problems. Okay, let's take a look at some questions that we might see, and then we'll take a look at a very handy tool, one of my favorite tools for diagnosing a probability problem, and it's a way to diagram it out. So if you stayed with me on Monday or Tuesday, you know, I showed you the two-way table. So I'm going to start with a two-way table. If you didn't stay with me, you saw the two-way table anyway, so because it was in the homework. And then what we're going to do here is we're going to look at how we could take this two-way table and use it to answer some other questions here. So let's take a look here. So I'm going to have a study that was done here where we have gender and then dominant hand. So we have lefties and we have righties. Okay, and then we will split this out by our genders. There's males, there's females. And in my study here, I had 3 males who were left-handed, and I had 20 males who were right-handed. And I had 4 females who were left-handed, and I had, 23 who were right-handed. So, and if you're with me again, you know that I like to have my totals figured out. So let's just figure out my totals. Let's see, this is 7. Obviously, this is 43. So we sum to 50. And this is 23. This is 27. So that also sums to 50. Perfect. So, you know, in this case, right, obviously, there's some conditional probabilities. Okay, because if I said, okay, what's the probability of, let's say, being left-handed? Well, that's 7/50ths. Okay, so 7/50ths is about 14%, right? If I said, what's the probability of being female? If we randomly selected somebody from this population, the probability they're female would be 27/50, okay, which is 54%. But if I asked you this question, what is the probability that they're left-handed given the person was a female? Okay, well, if that's the situation, then what we do is, as we look at our chart here, we say, oh, okay, so we're going to ignore the fact that anybody in the study was male. So we're just going to ignore that for a second. And we'll say, oh, okay, so the probability of left-handed given it's a female is 4 out of 27, which is 14.8%, so slightly higher than the entire population. So there we go. That's a conditional probability. It's given that the person was randomly selected as a female. So we're just ignoring the possibility that it could even be a male. And then we get 14%. Now, I want you to notice something, that is different than the other possibility, which is left-handed, or female given left-handed. Okay, check this out. What is the probability of female given they're left-handed, right? Well, that, as you can see, my friends, would be 4 out of 7, because we're disregarding the possibility the person's even right-handed. 4 divided by 7 tells us 57%, 57.1%. So totally different probability when we're talking about the probability that our randomly selected subject is female, given that we know they're left-handed. So that's just a real quick example of some conditional probabilities. Okay, that's how a two-way table could be used to figure it out. Okay, and it's a nice one because the two-way tables are pretty prevalent as we work our way through. So you should be able to do the OR probabilities like we did earlier in the week, and we should be able to do these probabilities using the two-way table because they do show up quite a bit. It is a very popular way to give a probability problem. Okay. But it's not the only way. So, and here's the other thing that I wanted to show you was my favorite way to diagram out a problem in probability is if I can use what's called a tree diagram. Okay, so a tree diagram, oops. Okay. Oh boy, Gracie has come to visit us. So she's over here. Hello, Gracie Grace. Thank you for coming by. Come on up. I'm sure the kids want to see you. Come here. Come on, hop up. Oh, she's being shy today, apparently. So she's not going to hop up so you guys can see her. Oh, well, she's just going to wander around my legs here for a minute. So I'll give her a quick scritch on the back and hopefully that will appease her. All right, so I'm going to read to you this prompt. It's on page 319 if you want to follow along. But the idea goes like this. It says, the Pew Internet and American Life Research Project found 93% of teenagers use the internet, and that 55% of online teens have posted a profile on a social networking site. Can you tell our book's a little out of date? Thanks. So there's a footnote for this. I haven't looked at it, but in a while to see what date this is from. But I'm imagining this is from a while back. You know, our book's getting old. It's 10 years old now, so it's getting up there. So what I want to do is diagnose this or diagram this out using what's called a tree diagram. And so I'll start off with it said 93% of teenagers use the internet. So what we're going to do is we're going to draw a little branch like this. And my first question is, do they use internet? And that is simply a yes or a no question. Okay. And then the next question, it says, 55% of online teens have posted a profile on a social network. So, do they have a profile? And this is also binary. Yes or no. Yes and no. And what we're going to do is we're going to label each branch of the tree with the appropriate probability. So it said 93% of the kids have internet. So that means what percent goes down here? Well, we know to be valid, it has to be 0.07. Right? And then of those who are online, so given that they're online, okay, that's a conditional probability. We know 55% had a social media profile. So that means 45% did not. So if they're not online, what's the probability, given they're not online, the probability they have a social media profile? Well, that would be 0. And so what is the probability that it's not? Well, that would be a 1. And then what we can do with this is we can then answer some questions. For example, we could ask the question like, okay, so what is the probability that a randomly selected 12 to 17-year-old, what is the probability a randomly selected 12 to 17-year-old uses the internet and has a profile online? Well, the cool thing about the tree is then you just multiply along the branches to get there. I know what that is. That's the probability they use the internet times the probability they have a profile given they use the internet. Okay, we know what the equation looks like. Okay, but with the tree diagram, it's so nice because I know that that probability for internet is 93. I know that probability for having a profile is 55%. And then we just a matter of multiplying those two together and you get, oops, sorry, type that in totally wrong. There we go. That's 0.5155. So the probability a randomly selected teen has both, uses the internet and has a profile is 51.15%. And so, the tree diagram becomes a really powerful tool to help us sort of diagram and then answer some questions that come from various probability things. Now, I will say this, they have their limitations. If you notice, that was only 2 events with just 2 outcomes, and my tree already got pretty big. It's filling up the screen there. The tree diagram works pretty well as long as you don't have too many outcomes and too many rounds of that. If I want to flip a coin 3 times, I could probably do the tree diagram, and it would be reasonable. We could do heads, tails, heads, tails, heads, tails, heads, tails, heads, tails, heads, tails, heads, tails. But you see, it starts to get pretty crowded pretty fast because there's got to be 8 outcomes after 3 flips. After one more flip, there's gonna be 16 outcomes. It gets really hard to keep track of the trees. Well, you can see what I'm saying. So after a while, tree diagrams become a little cumbersome, and I wouldn't suggest that you do that. For if I asked you like to what is the probability of, let's say, guessing all 10 questions correct on the next multiple choice exam, and there's 4 options A, B, C, and D for each question. You'd have 10 layers of 4 branches going up. It would be massive. It would be way too big to diagram out. So, it's not good for those kinds of things, but it is really good for small ones like like our coin flip, the internet one, and those kinds of things. So, all right, that's about it, guys. I did want to have one last thing here that if I take this equation here and through a little bit of algebra, it does reveal a way to calculate a conditional probability. You see the probability of B given A, if you just move the probability of A to the other side, you can move it over and get probability of A and B divided by probability of A. That will come in handy as you start working through some of the other problems that you have in the homework assignment. So that's it for today, guys. So thanks so much for coming in and checking out the and rule for probability. When we get to class, we'll definitely be taking a look at some more examples, and hopefully we'll see you guys there. All right, thanks for tuning in, guys. See you next time.